These second lectures will be to give you the main ideas, the main principle of stellar evolution. Actually, my first question will be, why stars emit light? Why are the stars bright? Many often when I ask this question to my student, there is somebody who answers, it's because there are nuclear reactions in the center. Actually, it's not completely true. If I had a button here which would switch off the nuclear reaction of the sun will not change. It will remain a star for at least 10, maybe 30 million years. So nuclear reactions are not essential for making stars. But as we shall see in a while, they are essential for making long-lived. So let us come back to the beginning. Why stars are bright? The first point is because they are hot, exactly as you are hot. Actually, I hope for you that you will have a temperature of 36, not so much above, and the room is around 20, 21. So since you are hotter than your environment, you are emitting energy. And it's why, in a while, we shall go for lunch to replenish this energy. And the stars are hot because, no, they are bright because they are hot. Now, why the stars are hot? Actually, it's because they are made of gas compressed by gravitation. I think that every of you have done to push air into your bicycle wires. And you have seen that the pump becomes hot. It becomes hot because you are compressing gas. You are giving mechanical energy to the gas, and this mechanical energy is distributed in the random movement, actually, of the gas. It increases the entropy of the gas. And what makes the stars to be hot is the fact that the gas is confined by gravity. If you look at the sun has a relatively well-shaped spherical shape. And its radius does not change with time, at least not in a human life. It will change over a longer lifetime. So we can say that a star is a sphere of gas confined by gravity. Now, if you have only gravity, what will happen? It will happen that all the gas will collapse to the center. And you can compute how much time it takes for the collapsing to occur. It will be very short. It's a time scale that in physics we call the free fall time scale. And this free fall time scale will be 30 minutes for the sun. So it's incredible. If there was only the gravity, the sun would collapse in 30 minutes. Why it does not occur? It does not occur because there is another force. This is mandatory. You cannot escape from this. There is another force which is actually the repulsion, or a microscopic force due to the random movement of the gas particle. You have on one side the gravity which makes this particle to concentrate to the center, and at the same time you have that the heat produced by this compression react by making a pressure force against the gas which is above and also below, by the way. Actually, it's like the air in this room which hit the walls, and this exerts a pressure on the walls. And if we put a bomb somewhere, it will make a very strong pressure wave which will maybe make the wall to go away. So you know, this pressure force, although it's a microscopic force, can be very strong. And you need it to prevent the sun to collapse in 30 minutes. Actually, I don't want to go too much into these details, but you can look into this very simple equation for those who are not too much afraid by simple physics, I would say. It's just the first equation expresses the fact that the gravity which makes the collapsing is balanced by a difference of pressure, what we call a gradient of pressure. You can obtain by just this hypothesis this relation which relates the pressure at the center of a star to its mass and radius. And you can then use what we call an equation of state, which tells you how much a pressure change when you change the density and the temperature. And here we use the perfect gas equation, which is relatively good for the Sun. And you can obtain the central temperature of the Sun, which depend on the mass and the radius, a little bit on the chemical composition. Actually, this work of obtaining the values of the central density and temperature for the Sun was already done a long time ago by Owen Lane at the end of the 1860s. And he obtained very interesting answers. He obtained that the temperature at the center of the Sun is 10 million K and the density 150,000 kilo per cubic meters. But here there was some, I would say, critical mind who said, oh, but is there not a problem here? Because you started from the hypothesis that the Sun is made of gas, and you obtain a density here which is much larger than the density of lead on Earth. So it cannot be true. On the other hand, he was correct. When we do models for the Sun, we obtain this kind of numbers. So what is the solution to this paradox? The solution is due to the very high temperature, 10 million K. And you know that when you have this high temperature, you change the structure of the bricks of the matter, in the sense that the atoms will lose their electrons. It means that the dimension of an atom that has lost its electronic cloud will be reduced by a factor 100,000. So you go from angstrom, 10 to the minus 10 meters for the size of an atom, to a Fermi, 10 minus 15 meters. So you decrease by 100,000. And so you can pack much more matter in a given volume. So what makes the whole story correct is the high temperature, which allows atoms to be ionized. So the story is that in a star you have at each point a force which makes the collapse, gravity, and another force which is a difference of temperature which counteract this collapse. The point is that because you need this gradient of pressure to go in this direction to balance the gravity, you need the random movement to be much faster here than here. Faster means higher temperature. So you have a temperature which is higher in the central part of the star with respect to the outer one. And if you have something hot in front of something which is less hot, you have a flux of energy, exactly as you are emitting energy now, you see? So we can say that the flux of energy in a star is a mandatory consequence of hydrostatic equilibrium. So we could say in a very summary way, the stars are bright because they are at mechanical equilibrium. So it makes a flux. By the way, it's very funny here to ask the question, are you brighter than the Sun? No, of course. But it depends on the point of view. You see, actually, you can do a simple computation. You can say, okay, the Sun is emitting a lot of energy. It's about like 4 10 to the 26 bubbles of 100 watt. Now the mass is also big. It's about 2010 to the 30 kilo. If you do the same for a human body, every of us, you emit light, or yes, light infrared, like a 100 watt bubble. Only one, with respect to 4 10 to the 26. So you are not brighter than the Sun. But you are much less weight, about 100 kilo. So per unit mass, you emit 10,000 times than the Sun. You see? So you are much more powerful, sophisticated object than the Sun. Okay. I will not also go too much into the details here because I know that some of you are not so, how to say that, have forgotten a little bit basic physics, but nevertheless, what the main point here is that you can compute the luminosity of a star, without any hypothesis about the source of this luminosity. So I can predict the luminosity of the sun without any nuclear reactions. I just to say, okay, the sun is at hydrostatic equilibrium, and this hydrostatic equilibrium tells me how much thermal energy is in the sun, because it is a thermal energy which balances the gravity. So I know the thermal energy. This will be, you can say this is the volume of the sun, 4/3 PR cube, and the mean energy in the radiation, in the energy that can be radiated, is about A, and it depends as the temperature to the fourth power. And you take here a mean temperature. Now, this is the content of energy in the sun. Now, if you have to have a luminosity, you can take this content, divide by the time scale for a photon to go out. And what is it? If you are a photon in the middle of the sun, you will have a very short mean free path, in the sense that you will make maybe you will fly for over 1 millimeters, and after 1 millimeter you will encounter a nuclei or an electrons, and you will change direction. So if you are a photon, you will diffuse once, and you will change direction here, and again here, and again here. So your track inside the sun will be a random path, I would say. So in order to have the luminosity, or the time for a photon to go out, you can take one of this interaction, or one fly between two interactions, which is the mean free pi L, divide by C. This is the time for going from atom 1 to atom 2, or from nuclear 1 to nuclei 2. And you have to multiply this time by the number of diffusion to go from the center to the surface. I will skip the point here, but it's something that you can find in the random movement. Actually, this number of diffusion can be simply obtained by taking the radius of the sun to the square, divided by the mean free path. Of course, here you will take a kind of average mean free path between the central part of the sun to the outer part, and to the square. You can remark that if there was interaction which were aligned along a radius, which never happens, because when the photon is absorbed, it can be re-emitted in every direction, you will have the radius divided by the mean free path. This is the number of diffusion to percourse the whole radius. But because of this change of direction, you have much more than this, and it goes to the square. Now, the mean free path of a photons will depend, or will be inversely proportional to the quantity of mass, of matter, per unit volume, the density. More you are dense, more interaction you have, and inversely proportional to the opacity. More opaque you are, more interaction you have. And if you do all this, you take the whole energy in the star, you divide it by this time, you obtain a luminosity. And if you use the temperature, how the temperature depends on the mass and the radius that we have seen before, using the hydrostatic the mechanical equilibrium, you obtain this relation between the mass and the luminosity. You obtain that the luminosity of a star depends on the mass to the cube. It depends inversely to the mean opacity and also to the chemical composition of the star. I don't have time here to go into too much detail, but here is what we call the mean molecular weight, which depends on which kind of stuff the star is made of. But you have seen, I have just used, I have not made any assumption about the source of the energy. I just said we have a thermal energy which is such that we have mechanical equilibrium. And we got this relation, and this relation can be tested. We can have, for some stars, the possibility to measure the distance, the luminosity, and the mass of the star. When you have two stars which are in a binary system, and the two stars are far away not to interact, then you can, by using the simple law, the simple Kepler laws, determine the mass. So you have the mass, the luminosity, and you can check whether it's correct or not. And it's correct. Okay. I skip this because it's okay. To go a little bit further. Now, The main point at that stage is that the luminosity of a star is a consequence of the hydrostatic equilibrium. Now, the main point of this slide is to say that this equilibrium has a price, which is the fact that the star loses continuously energy. And what happens now? What happens? Because if you lose energy, you change the structure of the star. And this is what makes the star to evolve. Actually, the stars evolve because their mechanical equilibrium implies a flux, implies a loss of energy. And this loss of energy changes the structure of the star. And actually here I have shown a kind of small experiment which could be a little bit of stellar physics in the laboratory if you want. You have a gas here inside this cylinder which has some temperature, and you have something which closes the cylinders with some weight. So you have the gravity and the pressure. And you have exactly what happens locally in the star. You have the gravity is balanced by the pressure. Now if you wait sometimes, the gas will lose energy. If it loses energy, the pressure will decrease. If the pressure will decrease, the weight will go down. By going down, it will give a little bit of energy to the gas. It will heat it. And we shall have a new mechanical equilibrium that will last for only a few minutes. So you will go from one hydrostatic equilibrium to another hydrostatic equilibrium, until you have lost the whole energy in the gas. How long can it last then? So you have not here the freefall timescale, because you have the force which compensates for the gravity. So you have another type of timescale, which is called the Kelvin-Helmholtz timescale, which is the timescale for a gas to go from one mechanical equilibrium to another. And this timescale, you can compute it for the Sun. Actually, it's nearly the binding energy of the Sun, gm squared divided by r. This is the energy in the gravitational binding energy of the star divided by L. And this is about 30 million years. And as you know, in the 19th century, it has been already computed, these numbers, and it has been believed to be the age of the Sun and also the age of the Earth. I think that Buffon has made some experiment by looking at how much time we have to wait for a ball of lead heated at different temperature to cool down at the present day temperature. And by extrapolating to a ball like the Earth, he got an age for the Earth, which was around 30 million years. And people have done this for the Sun, and they got the same age. So it was impressive to have the same age from different physics. But they are wrong, anyway. Actually, already at that time, people have noted that in order to, for instance, to dig a valley on the Earth, you need much more time than a few decades of millions of years. You need more, a few 100 million years. So there was something which was not correct here. By the way, this is the way to compute the Kelvin-Helmholtz timescale. So you need something else. If you have only gravitation at the source, because what we have used is a gravitation which heats the gas by making the weight to go down. You have to find another source. And what is this other source, which allows stars to live on longer time scale? This other source are the nuclear reactions. And this is why the nuclear reactions are not important for stars to exist. They would exist in a way, but are important for stars to exist on long time scale. In order for the Sun to exist for 10 billion years, you need nuclear reactions. This nuclear reaction occurs only in the very dense and hot part of the stars. They will not occur everywhere. You have no nuclear reaction at the surface of the star. At least you can have some elements which are destroyed at relatively high level inside the star, like for instance deuterium, lithium, boron. They are fragile elements which can be destroyed in the upper layers of stars. But the nuclear reactions, like for instance the transformation of hydrogen into helium, occurs only in 10%, for instance, of the mass of the Sun. Why it is the case? Because, of course, in order to make two protons to arrive at enough small distance to each other for nuclear force to occur, you need to overcome the repulsing force that exists in between a charged particle of the same sign. You know that an electron is attracted by protons, but two protons feel first a repulsive force, except then when they arrive near enough in order for the strong interaction force to occur. And in order to arrive up to this point, before the strong nuclear force begins to enter into the game, you need to allow the two particles to have sufficient high velocities. It's a bit like in this experiment where you have two balls that can glue if they arrive at the top and can touch each other. But in order to arrive at the top of this small hill, you need some initial velocity, which is above some level. It's exactly the same. Inside the star, you need some temperature to overcome the repulsive force of equally charged particles. Actually, the circumstances inside the central part of the Sun are not a priori, at first sight, not so favorable to this to occur. Actually, this is just a small computation. You know, if you take a temperature, T, this is just the same formula that we obtained a few minutes ago. This is how much kilo electron volt you obtain for a given temperature. So you have to put the temperature here in Kelvin degrees. And typically, if you have a temperature of 10 to the 7 K, you will have, yes, 0.001 keV. Oh, sorry, no, it's 1 keV. So why it's 1 keV? Ah, yes, because you have 10, so it's 10 minus 7, nearly 10 minus 7. If you put 10 to the 7, you have 1 keV. Sorry. So for a temperature which corresponds to the central part of the Sun, which is 10 million degrees, you have an energy which is available of 1 keV, which is a kinetic energy, which is the energy to go up to the hill. Now, the slope of the hill, or the Coulombian repulsion barrier, can be obtained by this equation, which is the potential, the electrical potential between two charges. One is Z1, the other one is Z2. So if we have two protons, we have 1 and 1. And it's 1.44 divided by the distance between the two particles, expressed here in Fermi. So if I put 2 Fermi, which is more or less equal to the dimension of the nuclei here, I need to go to a distance less than 2 Fermi. I need an energy which is at least 700 kilo electron volt. So you are far, far below, 2 orders of magnitude below what is needed. So according to this simple estimate, you should not have nuclear reaction of this type in the Sun, but you have. So what is the cause of that? There are 2 points. The first point is that, of course, this is a mean value. Actually, as you know, you have a distribution of energy. And this distribution is given by a Maxwellian distribution. And even if you have a mean value, you have a Q at high energy. But it's not sufficient. If you do only that, you mitigate a little bit this problem, but not enough. You need something else. And this something else was discovered by a professor first in Bern, Outermans, and then was again put in evidence by George Gamow, actually, the same of the Big Bang nucleosynthesis. They found a quantum effect which is the tunnel effect. Actually, the tunnel effect is the fact that instead of going up the hill, the particle will go through a tunnel, and so does not need so much energy to touch each other. If we plot here, yes, this is a very schematic plot which tells you that the nuclear reaction in a star will occur in a relatively small range of energy, which this small range is around what we call the gamma peak. Actually, when we do the computation of a nuclear reaction rate, we have to account for the Maxwellian distribution. And the Maxwellian distribution varies as E minus E over kT. And when we go toward high energy, we have a long Q, but we have a decrease of particle with this energy. On the other hand, you have this tunnel effect. This tunnel effect varies as E minus, this is, sorry, not so clear, but it's H divided by E. So when E increases, this becomes greater because we have a minus sign. And actually, the nuclear reaction will occur where we have non-zero value for the Maxwellian, and we are beginning to have a large value for the tunnel effects. Here we have a high value, but we have a very low Maxwellian. Here we have a high value, but a very low tunnel effects. So it's why we have nuclear reaction in this gamma peak. And the whole, I would say, work that our colleagues in nuclear physics are doing is to try to measure nuclear reaction rate in this domain. But it's very hard because in a star you have plenty of particles, you have a high density. In the laboratory you have a low density. And you have to compensate for this low density by using a high temperature. So you will make your measurement here. And you need to extrapolate to what happened here. And these extrapolations are based on complicated quantum physics computation that only a few people can master, I would say. And the point is that the majority of the nuclear reactions that we use in our stellar models are deduced from theory, starting from experimental value. So, actually, this is the same curves I showed just before, but reversed, where you have a binding energy. Actually, you see, in nature, every time you start from something which is not bound to something which is bound, you release energy. Typically, a very simple system is just a ball, and there is a hole in the ground, and you push the ball, which will fall in the ground. Actually, the system hole and the ball at the bottom is actually has a negative binding energy, because if you want to take the ball and put it again on the side of the hole, you need to make an effort. You need to provide energy to the system. So, and when the system formed, when the ball fall onto the bottom of the hole, it produced energy. At least some energy will come from the shocks between the falling of the ball in the bottom. You see? It is the same. Actually, when you have nuclear reaction in a star, you will start from hydrogen and you will produce helium. And helium is more bound than the nitrogen, than hydrogen. And it means that you will produce energy, you will release energy. And this energy will be equivalent also to the energy that would be needed to destroy helium. So you can use what I said before to compute the lifetime of a star during the main sequence by the transformation of hydrogen to helium. You can compute it in the following way. You can say you can take the mass of the star. Now, only a fraction of the mass of the star will be in condition favorable for nuclear reactions, and this is Q. For the Sun, it will be 10%. Now, not all this mass is made of hydrogen, only a fraction of it, which is about 70%. This is the mass fraction of hydrogen. So this is the quantity of hydrogen that participate to nuclear reactions. So it will be 1 for the solar mass, 0.1, 0.70. And each time you can put it in gram here, you have a fraction, you have gram here. And each time 1 gram is transformed into helium, you have 0.007 gram, which is transformed into energy. And you divide by L, the luminosity of the sun. And you obtain 10 billion years. So here you are safe. You are much longer than the 30 million years, which was very short. So it's why nuclear reactions are decisive for making the long lifetime of stars. Okay, here it's a bit, I don't know if I will have time to go into much detail, but nevertheless, if you want to resume in one sentence the evolution of a star is a contraction. sometimes fast, sometimes slow. It's fast at the very beginning, because at the very beginning, stars are formed by the contraction of molecular clouds. And this contraction occurs in very fast time scale, because only the gravity occurs. Then, once, due to the contraction, the star becomes hot and opaque enough for retaining part of the energy released by the contraction, you will settle into a state of mechanical equilibrium. And here you begin the nuclear lifetime of a star, the hydrostatic part of the evolution of a star. And at the very end, at least for the massive stars, the core will collapse again in a threefold time scale. But you can say that the life of a star is governed by gravity. Sometimes the contraction is slowed down by the fact that you are compensating the energy which is lost by the nuclear reactions. Actually, what is funny is that, you see, this is tracks which are computed with our code that we are using in Geneva Observatory, where we have different initial mass of the star. Typically, here you have 120 times the mass of the Sun. And what is represented is the evolution of the central density on the horizontal and the central temperature on the vertical axis. And you can see that when time goes on, actually time is going from the left here to the top here, you are contracting, increasing the density, and in the central part you are becoming hotter. In some way, it's a bit paradoxical, and in many ways stars are paradoxical, because you lose energy and you become hotter, at least in the center. So it's why we say that stars are some negative specific heat. You see, specific heat is the energy that you have to give to warm a gas by 1 degree, by the way. The energy that you have to give per unit mass. And in general, if I have a box full of gas here, I have to give energy to make a candle, to heat it, in order to warm up. And I can compute the quantity of energy that I have to give to warm up by 1 degree. But now we have loss of energy. And still it is heating because of this self-gravitating system. The gravity will compensate for the loss of energy, and this compensation will occur through contraction, which eats the gas. Okay, this is a bit boring, I am apologize, but it's a so splendid development that I invite you at least to read it. I will not go into the details because time is passing, but maybe I will just tell you the main idea, because it's so nice, you know. Actually, we have seen how we can compute the way the pressure depends on the mass and the radius, just starting from hydrostatic equilibrium. And you get that the pressure varies as mass to the square divided by the radius to the 4th power. Okay? Now you can say, okay, let us take a given mass which remains constant, a 1, a 2 solar mass, whatever. So the mass is not a problem. You can forget the m to the square. It's constant. But you look how the pressure increases if you make the contraction of the star. So you know that the pressure varies as 1 r over 4. If you take the logarithm of the pressure will be equal to -4 logarithm of the radius. If you make the derivation, d log p is equal to -4 d log r. And d log p is delta p over p. And d log r is delta r over r. So you have the first equation, delta p over p is equal to -4 delta r over r. What does it mean? It means that if you decrease the radius by 1%, you should increase the pressure in case you want to be still at mechanical equilibrium by 4%. You decrease the radius and you increase because there is a minus sign, you see. You can do the same with the density. Density is even more easy because the density is a mass divided by r cubed, and you can take the same play and you say that if you decrease the radius by 1%, you should increase the density by 3%. Now, by putting together, you replace delta R over R by delta rho over rho using the second equation, and you obtain this equation that says that if you increase the density by 1%, you need to increase the pressure by 4/3 of a percent in order to keep hydrostatic equilibrium. Here, you can use a very general way of writing the equation of state. Actually, in case of a perfect gas equation, alpha would be equal to 1, delta would be equal to 1. If you have another equation of state, alpha and delta takes other values. It's a general way of writing the equation of state, and alpha and delta are defined like this. If you do that, you can replace delta rho by delta P and delta T and find a relation between delta P and delta T, or delta rho and delta T. You can typically remove delta P and just have delta rho and delta T. And this is this equation that you obtain. Typically, for a perfect gas, if you put alpha equal 1, delta equal 1, you have 1/3. So you have that an increase of the density by 1% will increase the temperature by 1/3 of a percent. Now, if I come back to my tracks here, actually, according to the simple estimate I did, the slope between the increase of the temperature and density should be 1/3. And actually, the slope 1/3 is here. So you see, it's impressive. Actually, one can wonder why we need to make sophisticated models, I would say. But I will come back on that point here. But you have already a very good way, you see, of describing the main evolution of stars with this simple estimate. It's fantastic. Okay. Of course, now you can wonder how long it can continue. What makes the things to stop? You could imagine that it will last forever. But it does not, because at a given point, by changing so much the density, you enter into domain of the physics where new phenomena occurs. And we can have 3 types of phenomena. Of course, here it's a bit complicated to describe them in details. But what can happen? You can first empty the gravitational reservoir. The star can no longer contracting, cannot produce any energy by contracting. You can also empty the nuclear energy reservoir. You can no longer produce energy by reaction between charged particles. Or you can enter into instability regime where the photons become again energetic enough to produce pairs of electrons and positrons. And this changes the equation of state. And actually all these factors will at a given point stop the evolution of the stars or make it to become something else. Maybe I will just say a point about a given equation of state, which will be an equation of state of this type. Actually, this type of equation of state is the one that we obtain in degenerate gas. Degeneracy occurs when you have a very high density. And when you have a very high density, actually, what happens is that if you increase the density, you will force some particles to have very high energy levels because all the lower energy levels are already busy and cannot receive more, I would say, electrons. You see, if you are, let us suppose that you have a hotel and you begin by making busy the rooms in the first floor and then in the second floor, and you fill up the hotel from the bottom to the top. You can see that the increase of the pressure as the arrival of customers. At the beginning, you fill the first floor, then the second, and so on. And at a given point, if you receive still more customers, you have to put them at higher energy levels at the top of the hotel. Actually, it's a bit the same degeneracy. Degeneracy is based on what we call the Pauli exclusion principle. This is a kind of principle that says that you cannot put more than 2 electrons in the same room in this hotel. So after you have put 2 electrons in the same room, it's busy, and you have to go up in the floors. So actually, you have electrons that have to go up when you are at a high density, And their energy is not due to a temperature. It's not due to to the random movement. It's due to the fact that everything is busy below. So it's another source of pressure, which is linked to the density. And this is typically the relation between the pressure and the density that you have in a white dwarfs, in a non-relativistic electron-degenerate gas. Actually, in a relativistic electron-degenerate gas, you have the same type equation, but the 5/3 becomes a 4/3. But anyway, it's not so important. The point is that, you know, in a white dwarfs, the gravity is compensated by a gradient of density. Now, no longer by a gradient of temperature. So you have no flux in that case. The gradient, the particles which are at the bottom or deep inside the white dwarfs will not move outside because they are retained by the gravity. So there is no factors which produce a flux here. So a degenerate stars can stay forever in that state, unless there is some companion which will accrete some mass. Okay. What is interesting is that any star at a given point will have some part, especially the central part, which will become degenerate. Because of, as I said, the evolution of a star is an increase of the density as a function of time. So at a given point, a star will enter into this degenerate regime. And in this degenerate regime, actually, the two ways for a star to make energy, contraction, nuclear reaction, have a different behavior. Actually, maybe I will not go too much into the details because I would like to finish these lectures in 5 minutes now. But, you know, if we take the sun is producing energy by the nuclear reaction which occurs in the center. Let's do this kind of a thought experiment. Let us suppose that for whatever reason, at a given point, you transform a little bit more of hydrogen into helium. So you produce more energy. If you produce more energy, you eat the central part. If you eat the central part, you will produce more energy. If you produce more energy, you will eat the central part, and so on. And it's exploding sun. So why the sun is not exploding? Why it is stable? Actually, it is stable because of the equation of state of the perfect gas, which links the temperature to the pressure. Actually, when I said that if you produce more energy, you eat, it's true only for a while, because this heat will not remain. It will inflate the gas, because temperature is increasing, the pressure is increasing. So you inflate the gas. And if you inflate the gas, you decrease the temperature. So you slow down the nuclear reaction rate. So if you begin by accelerating the nuclear reaction rate, you arrive to a point where you slow down the nuclear reaction rate. So you have a kind of negative feedback. This negative feedback will not occur in degenerate condition because you have not this coupling between temperature and pressure. You see, because the pressure depends only on the density, the temperature can accumulate until it becomes explosive. So nuclear reactions are unstable in degenerate condition. And this is what makes type 1a supernovae, typically. The other point is that when you go into the degenerate regime, a contraction can cool the gas. You see, we have seen that in perfect gas situation, when the star contracts, you have a heating of the central part. When you increase the density by 1%, you increase the temperature by 1/3 of a percent. When you are doing the same in a degenerate regime, it's not the case. Actually, when you are increasing the density, the temperature can decrease. Why it is that? To say that with the hands, but here is before there is a demonstration in more mathematics. Actually, if you have a white dwarf, the electrons are degenerate, but not the ions. For instance, the nuclei of helium are not degenerate, so they have some temperature. Now, when I said that when a new customer arrives in this hotel, he has to go up. In order to do that, you need energy to go up. You need to take a lift, or the electron has to take a scale, so it will take energy. And this energy, where does it come from? It cannot come from the electron below, because they are locked into the room. It comes from the baryons which are on, which are not degenerate, and which will cool down. And this process is responsible for the minimum mass of stars. If you take a mass of 0.08 solar mass, 80 times the mass of Jupiter, typically. And if you compute the contraction of the gas, it will enter into the degeneracy regime before the central temperature is high enough for hydrogen burning to occur. So these stars will never burn hydrogen in their core. And this makes the mass limit of stars around 0.08 solar masses. Okay, so I arrived to my last view graph of these lectures. So I have indicated here some mass limit between different evolutionary history of stars. A point which is important to take in mind is that these numbers are very schematic. It's more complicated than this, and they depend on some parameters I have not spoken about. It depends on axial rotation of the stars. It depends on the fact that there is a companion or not. It depends on the mass loss. It depends on the convection. I have no time to speak about all these parameters. But we can say that between 0.08 and 8 solar masses, the star will become white dwarfs. This is the case of the Sun, for instance. I must say that a star like 0.08 solar masses will still be on the main sequence, even if it was born at the very beginning of the universe. 13.8 billion years after, it is still on the main sequence. So that no star of this type has yet time to evolve in our present-day universe. Actually, it's stars above 0.5 solar masses which have time to go beyond the main sequence in the lifetime of the universe. But these stars will become white dwarfs. Between 8 and 25 solar mass stars, we have stars which will produce probably neutron stars, and some of them will produce, and most of them will produce supernovae, explosion of the stars. Those stars will also go through a whole series of nuclear reactions and at the end produce black hole, maybe without any event. Maybe when the black hole forms, every mass is swallowed by the black hole with no supernova event. And between 150 and 250, the star can be completely destroyed by a phenomena called Pair instability. And above, there is a direct black hole collapse. Okay, you have here a view a little bit different, where different phases are indicated, but I will not so much describe this here. I will stop these lectures about the principle, and after we will speak about stellar nucleosynthesis. Okay.